Good morning, everyone. Happy Friday. So hopefully you're getting into the Kahoot. I'm going to give you about another minute to get into the Kahoot, but just a reminder, class starts at 8:15, so be here at 8:15 or even earlier so that you can, hear all the announcements that happen in the beginning and also so that you can join Kahoots whenever we do them. So just randomly throughout the semester, we'll do them, and they are for participation points. So the other announcement that I have is, okay, we had lab this week. Most of you guys lost points this week because what did you do? You copied blindly, right? You copied the lab textbook blindly without using your knowledge. So make sure you are using your own knowledge. Make sure you are thinking about the reaction and how we've done this in lecture. Think about the mechanism that you need to do. A lot of times there are typos in the textbook. I'm not going to tell you where they are because you should be finding them, right? You should be looking at the lab textbook and saying, okay, this isn't how it should be written, or this has too many lines on it. This should be hydrogens or whatever. Make sure that you are proofreading what you're writing, not just copying something blindly. We are going to do mechanisms, so you need to make sure you know how to do them so that you can do well in this class. All right, so that's going to be it. We're going to start our Kahoot now. It's covered by a square. Shouldn't be. All right, 10 more seconds. All right, so remember it's last name and then first name for everything in this class. The pen is at the bottom of the screen on the right. All right, so yeah, that was a Z alkene. The two groups were on the same side. So it was Z only for that. The two high priority groups were on the same side. So first place for that, CJ. Good job, CJ. All right. So now we are going to get into our lecture. And so we were already in this problem. We're going to just continue with what we were doing here. So as we were doing this reaction, remember, this is a dehydration, right? This is a dehydration, which is what we did in lab. And with this being a dehydration, it's a secondary alcohol. And so we said secondary alcohol, this is going to be E1 because it can do, it can dissociate. And so we show our lone pairs, H2SO4, that's just acid, a strong acid. And so we said in lab that we could just represent it as H+. So we just can write H+ to represent H2SO4. Instead of actually writing out, drawing all the bonds and everything, we just write H+. So from that lone pair to the proton, right? The arrow starts where we have electron density, and ends where we have a lack of electron density. So as we are drawing our product here, in this first step, we are getting an oxygen that now has 2 hydrogens on it, and a lone pair, and a positive charge. Now, what I'm doing right now, I really shouldn't be doing, because this is review, this is chapter 9 stuff, and I'm going through this mechanism. Even though it's from chapter 9, you should already know this. It's the beginning of chapter 9. Everyone learned this last semester, but I'm going to go through it. So know that as I do this kind of stuff where I have to go back over past things, then we're going to lose time for review for new things. So just keep that in mind as you're going over things. So when I say in lecture, this is from chapter 9, make sure you go back to review it if you're not sure about it. Anyway, we make a secondary oxonium ion. And so with our secondary oxonium, dissociation can occur. And so when dissociation occurs, we end up, so we can write minus H2O because we're losing water. Water is our leaving group. We end up with a positive charge there. So if I number this, 1, 2, 3, 4, 5, the positive charge has to be on carbon 2 because that's where my leaving group left from. So with this product, we have to think about something else. We have a carbocation, and so remember with carbocations, they can be arranged. And so if we have a hydrogen or an alkyl group right beside, we can do a hydride shift or an alkyl shift. So here, right beside our carbon 2, we go from the middle of the bond to carbon 2. Not from the middle of the bond to the middle of the bond. Middle of the bond to carbon 2, now we're doing a hydride shift. And so with a hydride shift, we are now moving that hydrogen over to carbon 2. So now we have a positive charge on carbon 3. So we moved a hydrogen over. Now, again, I don't have to show the hydrogen. We know that the hydrogen's on carbon 2 now in this second structure. We moved it over. Now, carbon 2 had 1 hydrogen as a carbocation, and then it has 2 when it is neutral. And so I have these 2 carbocations now that are both secondary, right? I have a secondary carbocation and another secondary carbocation equal in energy, so we can go between them. Can I access another secondary? Well, if I look here, I have carbon 4. There is a hydrogen here. If I go from the middle of this bond to carbon 3, I would do another hydride shift. Let's look at what that is, though. What is that? That's the exact same as this first one. So then we would number it from the other end. 1, 2, 3, 4, 5, getting to the carbocation as quickly as possible. And so hopefully you can see that this and this, these 2 are the same. So we really only have 2 carbocations that are possible here with the hydride shift. So with these 2, let's look at the different products that we can access here. So we have a carbocation here on carbon 2 or 1 on carbon 3. These 2 carbocations, are they going to lead to different products or the same product? Well, 1, 2, 3, 1, 2, 3. Looking at the different hydrogens we have, right, we look at the carbon that has the positive charge and we go 1 carbon away in all directions for any acidic protons. So to finish this, we're going to make a double bond. We have to look for acidic protons. So carbon 1 has a proton on it, and that's different from the proton that's on carbon 3. That has a proton on it as well. I'm going to call this A, and I'm going to call this B. Those 2 are different from each other. Now looking at carbon 3 that has the carbocation in this other structure, then we look at the 2 carbons on either side of carbon 3. So here we have a hydrogen, here we have a hydrogen. But looking at those 2, I hope you can see that those 2 are the same, right? Going through carbon 3, we have a mirror plane. So if I call this C, this is also C. Those 2 are the exact same hydrogen, right? They are equivalent to one another based on symmetry. So if I do this reaction now, then in the end, I'm going to have water coming in. I'm going to use water as a base. Those are lone pairs there. So from the lone pair to hydrogen A, let me see if I can get it to do dots a little bit better. There we go. All right, so from the lone pair to hydrogen A, from the middle of this bond into the middle of this bond. Notice that this is hydrogen A over here. That's still hydrogen A, but notice that arrow for a hydride shift is different from this arrow, from the middle of the bond to the middle of the bond versus middle of the bond to the carbon. Middle of the bond to the carbon, that's the hydride shift. Middle of the bond to the middle of the bond, we're making a double bond. And so there with HA, that's where we would be making this bond. So from HA, we would be making this bond between carbons 2 and 3. And we said that with that, we could also make this product our cis product, right? This is what we said last time. We're still making a double bond between 2 and 3, but as we make a double bond between 2 and 3, we can make the cis double bond or we can make the trans double bond. We said that trans is going to be major. Either one of these comes from HA though. And then from HB, I'm not going to show the arrow, but it's the same type of arrows, an arrow starting from the lone pair on water, ending at HB. That's how we would end up with this double bond, carbon 1, carbon 2, carbon 3. So between carbons 1 and 2, we have that double bond there. And so that's how we ended up with the other thing, the terminal alkene from HB. Now let's look at HC. If we deprotonated HC, they're both going to end up with the exact same product. What are we going to end up with if we deprotonate HC? From this lone pair to HC, from the middle of the bond into the middle of the bond, what are we going to end up with? The same exact thing as we had here. The exact same product. We're going to end up with, there we go, this product and this product, which we already saw when we deprotonated HA. So here, we don't need to show the hydride shift because the products that we get are going to be the same. You can draw it and make sure that the products are going to be the same, but here the hydride shifts don't give us different things. But let's say we had this. If I put this there, now we can get different products. So if we had a positive charge here, now we can get different products. If we had this carbocation, we can do a bunch of hydride shifts that will give us different products as well. I'll let you draw those. Again, this is review from 351. The very end of 351, we talked about our hydride shifts with our carbocation. So go back and review if you're not sure, but this is just to review that for you. But here with the two different carbocations that we could get with hydride shifts, they're going to lead to the same 3 products, the same 3 products. Questions on this one?
Wait, Dr. Navani, how many of the intermediate steps do we have to actually show for when we're doing something like this in a problem?
If you're doing a mechanism, you need to show all the steps. So the mechanism is, every single step that you see here. The hydride shifts, again, they're going to lead you to the same thing. So here, you don't have to show the hydride shifts, but these are 2 different carbocations. So I would say always draw the hydride shifts if you are going to get different carbocations, but here, they're not going to lead you to different products. The hydride shifts are going to give you the same 3 products with either carbocation, so it doesn't matter as much, but you need all the steps if you're going to show the mechanism. Any other questions? All right, then let's go on to our NMR problem. So this is how The NMR problem would be on, let's say, a problem set or possibly even the exam. You have all these numbers and letters, and you have to just say what all of this stuff means. So you need to use all of the data. In one way or another. All of it, every single thing here. So before we didn't really do anything with the molecular formula. Now we're even going to use the molecular formula. So let me show you how we break this down. So it's going to take me a while to do it, but it shouldn't take you a while. It's going to take me a while just because I'm talking through it, but don't let how long it takes for us to get through this one problem in class make you feel like these should be long problems. They shouldn't take you a super long time. If you're thinking, you can think a lot faster than I can explain every single step. So remember, when you're doing it, you will be able to move a lot faster than we move as we go through this, but let's go through this step by step. All right, so for one of these problems, the first thing that you always want to do is your degree of unsaturation. So our degree of unsaturation, remember, you need to have that that equation written down somewhere where you can access it quickly, but it's 2 times the number of carbons plus the number of nitrogens minus hydrogens minus X. What is X? Remember, that's the halogens. What? Oh, okay. Plus 2 divided by 2. Always plus 2 and always everything there divided by 2. So our degree of unsaturation for this problem, 2 times the number of carbons, so 2 times 6. And then we don't have any nitrogen, so then minus 10 for the number of hydrogens, and oxygens just don't show up there. So plus 2 divided by 2. So what is the answer here? How many unsaturations do we have here? Somebody unmute themselves. Tell me how many unsaturations. Do this math.
2.
2. So the answer here is 2. So what does that mean? That means we can have 2 rings, or we can have 2 pi bonds, or we can have 1 ring and 1 pi bond. Right? That's what the unsaturations are, rings or pi bonds. So remember what a pi bond is. That is where we're talking about having a double bond, so the second bond in a double bond, or the second and third bonds in a triple bond. Those are pi bonds. All right, so we start off there, and then we always go with our IR. Remember, IR tells us about functional groups. So if it's telling us about functional groups, that's a good place to start. So then we're not looking everywhere when we look at our proton NMR and carbon NMR data. So for the IR, we want to look at each number, and we're going to say what each number is. So 1635, we're going to say what functional group that corresponds to. 1710, 2930, 3095. So 2930, that's one that should just jump out, right? 2930, right below 3000, we said right below 3000, alkane. So we don't even really need to look that one up, right? We just should know some of these numbers just off the top of our head. So let's look at 1635. So 1635, if we look at these numbers, what could be 1635? Really only this, which would be the alkene, but it's specifically the carbon-carbon double bond of the alkene. That's at 1635. So we know we have an alkene. And then 1710. So 1710, that could be this. So we could have a carboxylic acid. Let's see, anything else? 1710. Oh, 1710 could be either an aldehyde or a ketone. All right, so you have to remember what these functional groups look like. So what does a carboxylic acid look like? Double bond to oxygen and then OH. What does an aldehyde look like? Double bond to oxygen with H, and then a ketone is just double bond to oxygen. So looking at these, is there one that we can say straight off the top, it's not this? Yeah. It's not a carboxylic acid. How do I know it's not a carboxylic acid? Because I only have one oxygen, right? Looking at the molecular formula, I only have one oxygen, so I know it can't be something that has CO2H. That's a carboxylic acid. I know I can't have two oxygens. I have to only have one, so it can only be an aldehyde or a ketone. And then we have 3095. So we said right below 3000, that's our alkane. So right below 3000 alkane, right above 3000, that's our alkene. So this is right above 3000. So we have the alkene. But what kind of alkene is it? It's really the carbon-carbon double bond, but there's a hydrogen there. It's that portion of the alkene. It's the carbon-hydrogen of the double bond. So what did we say about our degree of unsaturation? We said we could have two rings, two pi bonds, one ring, and one pi bond. Look at what we have here. We know we have an alkene. An alkene would be one pi bond. We also know we have either an aldehyde or a ketone, so we know we have a carbonyl. That's what this is called, a carbonyl. So we know we have a carbonyl. Well, what is this? This is a double bond. And so we know if it's a double bond, it has a sigma bond and it has a pi bond. And so we know for a carbonyl, we have one pi bond. And so what are we looking at here for our degree of unsaturation? That 2 corresponds to 2 pi bonds. We have a pi bond for the alkene and a pi bond for the carbonyl. Those are our 2 pi bonds. So if you draw a ring, you know you have drawn the wrong thing. If you have another pi bond, you know you have drawn the wrong thing. In the end, you can only have one alkene and one either aldehyde or ketone based on what we're seeing here with the degree of unsaturation and IR. Questions on what we've done so far? All right, so we've used all of our data. We've used the molecular formula to do degree of unsaturation, and now we've used all of our values in the IR. Don't leave one. If you leave one, you lose the points for all the IR. If you don't do the degree of unsaturation, you lose those points. Everything has points associated with it, so you don't want to lose any of those points. All right, let's move on now. Now we're to our proton NMR. So proton NMR, here this is dissolved in CdCl3. What is that? Deuterated chloroform. Remember what deuterium is? 2H, right? That doesn't show up in proton and 1H NMR. Only that isotope shows up, not the 2H isotope. But anyway, looking at this, we want to use all of these numbers and we want to give these, we want to assign each to a building block piece. So we have our data here. So get out your IR NMR sheet if you don't already have it out beside you. I'll give you 20 seconds to get that out. All right, so we have our IR NMR sheet. Remember, we're using this to figure out chemical shifts. If we get a chemical shift that is an alkyne chemical shift, obviously that can't be true, right? What do we see in our IR? Alkene, aldehyde, ketone. That's it. So whatever we're seeing here has to be alkene, aldehyde, ketone, or alkane. That's it. It can't be anything else other than that. Okay. So we also can't have alcohol here, right? There's no alcohol in the IR. All right, so looking at this, we want to start off with our first one. So whenever we're doing a building block piece, start off with the integration. How many hydrogens? So 3 hydrogens, which means we write CH3. And then we draw an arrow to those hydrogens and label them accordingly. So that we know these are the hydrogens we're talking about. We're talking about these 3 hydrogens that have a chemical shift 1.66. So looking at this, it's a doublet of doublets. Remember what doublet means? It means it has 1 hydrogen neighbor. with that, we see we have these J values. And so these J values are going to be really good for helping us figure out what is going on here. So we need to look at our J values. We also need to look at this chemical shift. So this is a CH3. When we look at where a regular primary alkyl, just a regular CH3 would show up, 0.8 to 1.0, this is deshielded, right? It's downfield. 1.66, it's downfield. So what could that possibly be? There's something pulling away electron density. And so we have here 1.66 is probably here in this region where it is allylic. So the hydrogens would be beside the double bond, would be beside the double bond. So that means that as we draw this, we're going to draw this as a carbon that's in a double bond to another carbon. Now I left space there for a hydrogen if there is one there. Let's look. This is a doublet of doublets. So yeah, there's going to be a hydrogen on the carbon directly beside this CH3. So we know that this is allylic. That's what we just found out. And it's these hydrogens right beside a carbon of a double bond. All right, so we have, this is a doublet of doublets, which is kind of crazy because usually when we had doublet of doublet, that meant one hydrogen neighbor on this side, one hydrogen neighbor on this side, right? On either side. But now we're seeing a doublet of doublet. We don't have any more sides for the CH3. There's no more sides. So where could this be? So we have a 2 for a J value, and we have 6 for a J value. So let's figure out what each of those are. So looking here, we have our ranges, we have our typical. So here, typical, probably what we're looking at there is this non-coupling, and probably what we're looking at is this allylic coupling. None and allylic. So what does none mean? Well, none means they have this pink hydrogen that's beside the blue, and the blue is a hydrogen on the double bond. So looking at this, which hydrogen is the pink hydrogen? Which hydrogen is the blue hydrogen? Which one is 1.66? Would that be the pink one in this scenario or the blue one for this non-coupling? Well, 1.66 is probably the pink hydrogen, right? Because it's not on a double bond. So if we go back, 1.66, that's our pink hydrogen. That is coupled, and so I'm going to draw this where I'm showing these two are coupled to one another, and I'm going to label the J value. This is the J equals 6 hertz. These two are coupled to one another. From the J value, I have that non-coupling, and so from that, looking at your sheet, that non-coupling, this pink hydrogen on there, well, yours isn't color-coded, but let's look back here. The pink hydrogen here is that CH3, and the blue one is the hydrogen on that double bond. So now we have this other one. The other J value here is 2. And so with 2, that's allylic. That's where we have a hydrogen that is coupled far away. It's coupled to another hydrogen that's 3 carbons away. And those 3 carbons have to be going through a double bond. We have to go through a double bond to go from the pink hydrogen to the blue. Again, look at the structure, the building block piece that we've drawn. What does 1.66 have to be? It has to be the pink hydrogens, because 1.66 is not on the double bond. So 1.66 has to be the pink hydrogen here. So they're showing just one, so it could be 1, 2, or 3 hydrogens that are pink here, but in this case there are 3 pink hydrogens coupled to a hydrogen that is 3 carbons away. So 1, 2, 3 carbons away, that means there has to be a hydrogen here, at least 1 hydrogen. So looking at this, it's a doublet of doublets, meaning that there is 1 hydrogen neighbor. So notice I drew that blue one there. I'll draw another blue one, again, from this hydrogen now to this hydrogen. This is our J equals 2 hertz. So we have non-coupling and we have allylic coupling. Allylic is this long-range coupling, 3 carbons away. So the CH3 and then 3 carbons away. Now through the double bond, those two can see each other. We usually didn't see that, right? We didn't see that before when we had single bonds, but now we can do this long range coupling. So now I have shown everything that I can show with this building block piece. I've shown that it's 3 hydrogens. I've shown why we see this chemical shift being so deshielded. I've shown why it's a doublet because it has 1 hydrogen neighbor. I've shown why it is another doublet because it has another hydrogen neighbor. And I've shown why it is a J value of 6 and a J value of 2. I've shown everything here in this building block piece. Now I can move on to the next one. That's one piece of data that you have to have, everything you see there. Let's move on to the next one. All right, 3H, so I'm gonna write CH3. And I'm gonna draw the arrow to those hydrogens and label them as 2.12. Again, think about this chemical shift. It's too far downfield. And since it's too far downfield, what do we have to have? We have to have something beside it that is pulling away electron density. Now look at this, it's a singlet. So that means it is beside a carbon that has no hydrogens on it, right? No hydrogen neighbors. But why is this so deshielded? Well, let's look at our values here. Again, we would expect it to be here at 1 at the highest, but it's not, it's 2.12. So where could that be? Well, that could be here in this region. So what you see here, it's called ketone, but I'll put ketone in parentheses. Ketone really means any hydrogens on a carbon beside a carbonyl. A carbon with a double bond to oxygen. It doesn't have to be a ketone. It could be an aldehyde. It could really be a carboxylic acid. It could be an amide. It could be anything that has that carbon with a double bond to oxygen. So when you see ketone, don't assume it has to be a ketone. It could be other functional groups. It's just any hydrogens on a carbon beside a carbonyl. Make a note of that in your notes. So really, when we see 2.12, this is okay, but really it's going to be this, where it's a CH3, 2.12, and it is beside the carbonyl. This is the building block piece that you need to have. This is what you need to have. Why is it a singlet? Because it's a carbonyl. There are no hydrogens on there. So when I'm drawing these, I always will show these open spots. So I have an open spot here. If I go back to my first building block piece, on this carbon, I'm showing 1, 2, 3 bonds. So I have an open spot that I have there as well. These open spots are going to be what helps us to piece everything together. When you think about a puzzle, with a puzzle, if you can't see where it's curved on one end or where it's flat on other ends, you don't know where you could piece things together. So having these open spots will help you. So make sure you show places where we can make more bonds, because we have these pieces, building block pieces, we want to put them together. All right, so we've done 2.12. It's 3 hydrogens. It's a singlet. Why is it 2.12? Because it's right beside a carbonyl. So really not this. This is how we would draw that building block piece. All right, moving on to 2.60. So 2.60, 2 hydrogens. So we want to write a CH2 and draw an arrow to those 2 hydrogens, not to the carbon, to the hydrogens. We're talking about hydrogens. This is only hydrogen NMR, not carbon NMR. So draw the arrow to the hydrogens, and we're going to label them as 2.60. Now, how many more open spots do we have on this? We have 2 more open spots for this carbon, right? If it's making 2 bonds, it has 2 more bonds that can be made. All right, so looking at this, it's a doublet of doublets. So what you could do is just this, CH on one side, CH on the other side, and try to go on. But you haven't thought about these J values. You haven't thought about your chemical shift. So this is really what we don't want to do. We want to go more in depth with this. We want to think deeper about this now. So we have our CH2, 2.60. Let's look at 2.60. So 2.60, what kind of a chemical shift is that? look at where it's showing up. Again, in this ketone range. It's at the high end of it, so that means there might be something else that's also pulling away electron density. So that means that we probably have carbonyl right beside that. Probably have the carbonyl right beside it because of this value, 2.60. It's de-shielded. Now looking at these J values, 2.2 and 7, let's go investigate our J values. So 2.2 and 7, these are typical values, but the values can be in that range. So 2.2 would probably be in this range, and 7 would probably be in this range. Close to 6, but it's 7. So that means we're seeing something similar to what we had before. So I don't need to explain all this to you again, but looking at this CH2, would it be the pink hydrogens or the blue hydrogens? CH2 would have to be the pink hydrogens. We can't put 2 hydrogens onto this carbon. It can't fit 2 hydrogens, so it can't be a CH2. This has to be the CH2. Also, think about the chemical shift. The chemical shift isn't high enough for this 2.60 to be the blue. The chemical shift is way too low to be a blue hydrogen on a carbon with a double bond. So if that's true, then here we have a CH, right? It is a doublet of doublets. So there's a CH where this carbon is in a double bond to another CH with another open spot. Why do I know all of that? Based on those J values. So let's look at them. We have from here to here, that is going to be J equals 7 hertz. That is that non-coupling. And then again, from here to here, that's going to be my 2.2 hertz. So let me pause here and show something to you. When you're looking at this peak, 2.60, every single thing that you see with 2.60 has to start with 2.60. Everything is with respect to 2.60. So if you're going to draw and you're going to show, okay, these two things are coupled to each other, you can't couple anything. So I'm going to draw something in red. This is not true. You can't do 2.60 and say, oh, these two are coupled to each other. They can't be coupled to each other in 2.60. Everything has to be with respect to those hydrogens that we labeled as 2.60. So anytime you draw this, showing this J value coupling, or when you're showing here, okay, this is split into a doublet because of this, this is split into a doublet because of this, everything has to be with respect to the hydrogens in that peak. So everything here is with respect to 2.60. When we were doing 1.66, everything I drew was with respect to 1.66. All right? So don't add in J values trying to do other things. Just stick to what you're looking at here. Start with 2.60 and look in all directions for what you are coupling to that. All right. So we are looking at 2.60. We said that 2.60 is de-shielded because it is what we would call ketone, but really right beside the double bond. But it's also de-shielded because it is allylic. Both of those things are happening. On one side, electron density is being pulled away because of the carbonyl. On the other side, electron density is being pulled away because of the double bond, and so it gets de-shielded and de-shielded even more. Look at 1.66, right? It's de-shielded a little bit, but it gets de-shielded even more if it has both a carbonyl and a double bond. Look at 2.12. It's de-shielded, but if it had both things, then it would be de-shielded even more. It's an additive effect. So we have 2.60 here because we have de-shielded it having the double bond, and we've de-shielded it even more having the carbonyl. So it's ketone and allylic versus this one, which is ketone. Versus this one, which is just allylic. All right, now let's look at 5.22. So 5.22, we are now here downfield where we're looking at alkene hydrogens, right? 4.6 to 5.7. So about maybe 4 to 6, we'll say, for the alkene hydrogens. So that means we can draw this just straight up. We can just draw this for 5.22 as a carbon with a double bond to another carbon, and we can label this as 5.22. We know that because this is an alkene, in the alkene region, we can just draw the alkene and add in that hydrogen. It's one H, so it's one hydrogen on this carbon, and I'm going to draw in the other open spots I have there. But 5.22 is split into a quartet of triplets of doublets. So what does that mean? It means on one side it has 3 hydrogen neighbors, somewhere else it has 2 hydrogen neighbors, and somewhere else it has 1 hydrogen neighbor. All 3 of those neighbors give it a different J value. All 3 of those neighbors give it a different J value. So let's look at 5.22. Let's look at these J values to figure out what has to be where. So we have 2.2, 6, and 10 hertz. All right, so 2.2, oh, we've already seen 2.2. We said that was allylic. We also have 6. We've already seen 6. We said that was none. The only one that we haven't seen is 10. And so 10, remember, this is cis to one another. It doesn't have to be a cis alkene. It just means that these hydrogens are cis to one another. So let's take all this information here. So cis to one another, 10 hertz. We have our non-coupling where this 5.22, would it be blue or would it be pink? It would have to be blue, right? 5.22 would have to be blue here because it's on a double bond. Here for allylic, which one would 5.22 have to be? Again, blue, because it is the hydrogen on a double bond. So let's go back here. We had 10 hertz coupling, which was cis. So we're going to draw in a hydrogen that is cis to the hydrogen that we have drawn. And I'm going to label this as 10 hertz. 5.22, cis to 5.22. It has to be cis to 5.22. That is going to be a 10 hertz coupling. So now we have non-coupling. So if you're looking at your sheet, what is the non-coupling? It's on a carbon directly beside the carbon that has that hydrogen on it. And so here, we can add in a carbon there, and we have some number of hydrogens there. So we can either put a quartet or we can put a doublet. So how do we know which one we would put here? Let's go back and think about the other side of 2.2 and 6. Where did we see 6 before? We saw 6 here with 3 hydrogens. Where did we see 2.2 before? We saw 2.2 with 2 hydrogens. So those J values have to go with 1.66 and 2.60. We're seeing it from the other side. Remember, we said we were seeing it from one direction, and then we look at it from the perspective of the other thing. Now we're seeing 6 and 2.2 hertz from the perspective of the 3 hydrogens and the 2 hydrogens of those other peaks. So if we're thinking about this having to be 6 hertz coupling, it's going to be CH3. How do I know that's the CH3? So let me draw this in. From this hydrogen to this hydrogen, that's 6 hertz. How do I know that is? Because I already saw this from the perspective of 1.66, so I know that I can label these hydrogens as 1.66. Right now I'm looking at everything from the perspective of 5.22. 5.22 has 10 hertz coupling and a 6 hertz coupling, but I can look back at 1.66 to say, okay, what was 1.66? 1.66, if we go back here, it was this CH3 beside a carbon with a hydrogen on it. So I know what this hydrogen is now. I know that hydrogen, if I'm seeing 6 hertz here, and I'm seeing 6 hertz here, I know that I'm talking about the same thing. So I'm seeing 1.66 and I'm seeing 5.22. That has to be 5.22. because I'm seeing it from the other side. So for 1.66, those 3 hydrogens, 6 hertz, go here. 1.66, 3 hydrogens, 6 hertz to 5.22. All right, so I've only shown 2 of my couplings. I still have the 2.2. We said the 2.2 is this long range allylic coupling. And so here with that, this would have to be, the blue one here would have to be 5.22, and then the pink one would have to be what we've seen before. So we are going through from 5.22 through the carbon to another carbon, 3 carbons away, 2.22. That has to be the 2 hydrogens that are 2.60. So from 5.22 all the way over to these 2 hydrogens, that is going to be my 2.2 hertz coupling. The further away the coupling is, the lower the number is. The further away the hydrogens are from one another, the lower the number will be. So now I've shown everything that I can for this building block piece, other than saying that, okay, we have one more open spot here. I remember I want to show all my open spots, so I want to make sure I show this open spot here on this CH2. If you're paying attention, we could finish it right here. We basically know the structure. If you're paying attention to what you're doing, we're looking at everything from different perspectives. You can see here, hopefully, how this can be pieced together, but let's do the last one here. 5.59, it's 1 hydrogen. 5.59, again, we have to draw this as a carbon-carbon double bond because of where that chemical shift is. 5.59, that chemical shift, actually, let me not do it this way so that you can see it a little better. Let me label a different hydrogen as 5.59. I'm going to label this one as 5.59. Why am I doing that? Because we're going to see everything that we just saw, but from a different perspective. And so I want you to be able to see that from a different perspective. But anyway, we have here 2 hertz, 7 hertz, 10 hertz. We know what 10 hertz is. 10 hertz coupling, that's the cis coupling where these 2 are cis to one another. We've already seen that. And so we know what this hydrogen is over here. We know this has to be 5.22. It has to be 5.22. We already saw 5.22 had the 10 hertz coupling, and so we're seeing it from the other side. So 5.59 now, we're still looking at 5.59, so that's why it is a doublet. So we've shown why it's a doublet, but why is it a quartet? Why is it a triplet? Well, because of the 2 hertz and the 7 hertz coupling. So 2 hertz coupling, allylic. 7 hertz coupling, none. We've seen these already before. So the none coupling, that'll be closest to 5.59. So what do we have to have there? We're talking about 7. Where did we see 7 hertz coupling before? With the 2 hydrogens of 2.60. We've seen this before. So this, from here, these hydrogens to this hydrogen, 7 hertz. The last thing we have to show here is, why is this, so we've shown why it's a triplet, why is it a quartet? And why is it 2 hertz coupling? Over here, we have these 3 hydrogens. We know these 3 hydrogens are 1.66, but from here, from these hydrogens over here to 5.59, that is our 2 hertz coupling. That is our 2 hertz coupling. Questions on any of these building block pieces? Or from the previous slide also. Questions on any of these?
Okay, Dr. Nobanian. So
Okay.
okay, hold on. So why are we adding the J values again? Because I mean,
How would you even be able to figure this out without a J value? Without J values, you would think this, right? Based on what we were doing before, if we look back at 2.60, that's what you would write. You'd write, okay, I have two hydrogens, it's a doublet of doublets, so I have a CH over here, I have a CH over there. But look at what it actually is. It's not like that at all. It's a CH and then a CH over that direction, which we weren't doing when we had alkanes. We can only do this because of the double bond here. So there's no way that you would be able to figure this stuff out without the J values. You wouldn't be able to piece this stuff together in the right way.
okay.
The J values actually help us more. If you didn't have a J value, how would you figure out the stereochemistry here? How would you figure out what's happening here? Because you have this long range coupling through the double bond, these two hydrogens have to be cis to each other. Are they trans to each other? Are they cis to each other? You can't figure this stuff out without these J values. So the J values, even though they complicate things, they're actually a gift to you because they help you to figure out things and a little more clearly. So when we look at this kind of helps us to see, okay, this is how the molecule is set up. If you can reason it out, which one's a pink one, which one's a blue one for each building block piece, for each J value, then that helps you to put together your building block piece and put in, okay, this J value goes here, this J value goes here. So really the J values, even though, yes, they kind of complicate things, they also are helping you to see how the structure is put together. Other questions?
I had a question. Last semester when we did these problems to show how many hydrogen neighbors, if it was a doublet, we'd have to show the 2 minus 1 equals 1 neighbor. Do we still need to show that in our work?
No, you didn't have to do that math. You didn't have to do that. If it was a doublet, so before, if it was just like, okay, 3H comma doublet, before all I needed to see was, okay, CH3, draw an arrow. So let's say this is 0.9. So we label this as 0.9, and then, okay, it's a doublet, which means there's one hydrogen neighbor. This is all I needed to see. And if this is how the piece looks, that's all I need to see still. But if now we start adding in things with where the chemical shift is higher, you need to tell me why it's so deshielded. You need to show me in your building block piece why it's deshielded. And then when you have J values, you need to show me why these J values are what they are. So show me why it's deshielded and show me why the J values are what they are, as well as how many hydrogen neighbors, what is the integration? Show me all that in your building block pieces. But you didn't have to show me math per se. Last semester, you just had to, if you just draw this, that tells me that's one hydrogen neighbor.
Okay.
Other questions?
I have a question.
Uh-huh.
So, when we got to the final step, and you said you should know what the molecule looks like, if we were doing this in like the learning assessment or whatever, do we have to show that final step even though we know?
You do need to, I need to see these J values. So I need to see the J values from the perspective of both things. I also need to see stereochemistry. So I have to see this stereochemistry here where these two hydrogens are cis to one another. Before, when I was doing this, I was just saying, okay, there's a hydrogen here and there's a hydrogen here on the double bond. But you need to then expand it. Once you know, okay, this is a 10 hertz J value, I need to see that J value. It's going to be way too complicated to try to throw everything in, but you need to show me the stereochemistry for the J values. You need to show me that this is 1.66, this is 5.22. Within that J value, I need to see it from both directions so that I know you understand it from both directions. But if you can, if you're looking at this, and you can, instead of doing this, you can just go over here and do this kind of thing, that's fine. If you want to have it all expanded and you're like, this is 1.66, I'm seeing this 6 hertz, and I'm also seeing, you know, that's fine. I need to just see this kind of stuff here where you're showing me here, these are the J values, here's the stereochemistry, here's why this is deshielded. I need to be able to see all of that. But yeah, what I was saying is once you get to this stage, you should probably be able to see that this is true, and then just quickly throw the J values onto it, onto that structure. If you can fit it on here, then okay, but it gets pretty complicated. if you're trying to do all these, you know, lines connecting things across each other. But if you can fit it all on there, that's fine, and you can just add on to the first structure here. Other questions? All right. So with this, I just showed you these long-range couplings. In general, we're going to ignore these. I just showed you them to show you how much more complicated the structures get. But in general, I will ignore these, and I'll tell you that I have ignored them on an exam or on a problem set. I'll write, ignore long-range alkene couplings. All right, so yes, we were dealing with 2 and 2.2. In general, I would ignore those. All right, so what do we have here? We basically have these 2 building block pieces. In the end of everything that we did there, we end up with this as a building block piece, and we end up with this as a building block piece. These 2 hydrogens here on the same side as one another, cis to one another. We have a CH3 and we have a CH2 with 1 open spot. That's what we ended up with, right? If we bare bones everything else that we did, then this is what we end up with. We have 1 open spot here, we have 1 open spot there. Piece those 2 things together. After we've done all this, it is so easy to put together the final structure. And so for the final structure, I need to see your final molecule where you assign all of the carbons and all of the hydrogens. So hopefully you can see how basically this was what we needed to do. Bring together the carbonyl and the CH2 to make this bond. And now we need to assign all of the carbons and the hydrogens in the structure. So you don't have to show me the J values again. You just need to assign all of the hydrogens. So draw an arrow to all the hydrogens and draw an arrow to all the carbons. So let's do our hydrogens here. So we had 5.22. We had 5.59. We had our CH2 as 2.60. Our CH3 over here as 1.66. And our other, oops, that says CH2, should say CH3 here. Our other CH3 is 2.12. So those are all of our hydrogens. Now we need to assign all of the carbons. So looking at this, I tell you how many hydrogens, and so this is the kind of information you would get from DEPT, right? We talked about the hydrogens, the odds, the evens, and how they are. That's how we know this is a CH3, this is a CH3. So we have 2 CH3s, 22 and 30. Which one do you think would be more deshielded? Well, looking here, we have one of them being allylic, and then one of them being beside the carbonyl. So we have here allylic between 20 and 40. Our carbonyl is going to deshield, but it's not showing that data on here. But anyway, so we have 22 and we have 30. 30 is actually going to be this one because it's close to this carbonyl, which is more of an electron withdrawing group than a double bond. So we have 22 for this one. Then we have our CH2. That's easy, 35 CH2. We only have 1 CH2 here, so 35. Then we have our quaternary carbon. What is quaternary carbon? It means carbon with no hydrogen, so 193. And if we look at the sheet here, aldehyde ketone, 190 to 210. So 193, that fits in the range. The last thing we have would be our alkene. So 100 to 160 is where we would expect the alkenes. And so we have 117 and 121. Looking at the value, 5.59, closer to the carbonyl would be more deshielded. So that would be 121, and this would be 117. So this would be what I need to have in the end. All right, questions here?
Could you explain the CH3? Why that one is 30? Why the other one?
You'll see later, but the oxygen is more electronegative than a carbon. And so a carbon-carbon double bond, it's just slightly pulling away electron density. Oxygen actually is an electronegative atom, and so it can actually pull away electron density better than the carbonyl. So that means that this is going to be more deshielded because of this, because of that partial negative there. All right, so that's all the work I need to see for a problem like this. I will make your problem set. We finished earlier than I expected, which is good because then we possibly will have a little bit of time for review. I'll make your problem set available, and it'll be due on Monday before we have lectures, so you have the weekend to work on that. If you don't know about problem sets, remember, work on it on your own, work on it together with your group to come to a consensus on each answer, all right? I'm gonna stop after we finish here. I'm gonna make it available on Blackboard under assignments, and then you would turn it in there as well. One problem set with all the PDFs, one PDF with all your problem sets in it for your group, and make sure that the first one that I see, that's the one that you want me to grade. That's the one that I'll mark everything on. All right, if you have more questions about the problem set, you can email me or ask other people who were in my class last semester. All right, you guys have a great weekend. Be safe. I love you guys. I'm praying for you. You can do this.
Thank you.
Bye. If you have a question or two,
Thank
you can
you.
stick around. I do have a couple minutes to stick around. So if you do have questions, stick around. Bye, you guys.
Thank you. Bye.
You're welcome. Bye.
I have a question.